Hello students, welcome back to this lecture, One Real Numbers. So in this lecture, basically we will discuss about uh, root 2, root 3 is irrational numbers. Okay, root 5 is a irrational number, and in general, root p is an irrational number. Okay, so let's get started. So in this example, we will prove that root 3 is irrational number. So in our previous lecture, we have proven root 2 is irrational number. Okay. So there basically we use method of contradiction. Okay. So for proving root 2 is an irrational number, there we first consider root 2 is rational number. Okay. So since root 2 is rational number, then we can find two integers s and t, and we can write root 2 as s over t, root 2 as a fraction s over t, where t not equal to 0. Okay, and if s and t have common factors other than 1, then we can divide by common factors, then we'll get root 2 is equal to a over b, where a and b are common, a and b are co-prime. That is, GCD of a and b is equal to 1. That means the numbers a and b have no other common factors other than 1. Okay, and then we'll get root 2 is equal to a over b, and if we cross multiply them, then we'll get root 2 times b, this is equal to a, and now if we squaring and rearranging, then we'll get 2b square is equal to a square. Okay, so from this equation we can say 2 divides a square, and we know this theorem: if p is a prime numbers and p divides a square, then p also divides a. Okay, so here 2 divides a square. So by this theorem we can say 2 also divides a. Okay, so since 2 divides a, then a can be written as 2 times c for some integers c. Okay, now if we substituting the value of a is equal to 2c in equation b square, 2b square is equal to a square, then we'll get 2b square, this is equal to 4c square. Okay, and that is b square is equal to 2c square. Okay, and it implies 2 divides b square. Okay, and if we use the previous theorem, if 2 divides b square, then it implies 2 also divide b. Okay, so here we see 2 divides a and also 2 divides b. Okay, so here a and b, therefore a and b have common factor as a common factors. Okay, so but this contradicts our assumptions, since we actually assumed a and b have no other common factors other than 1, but we get here a and b have 2 as a common factors. Okay, so basically this has arisen the contradiction, since our assumptions actually false. Our assumptions root 2 is rational number is our false assumptions. Okay, so we can conclude root 2 is an irrational numbers. Okay, so this is how we'll also prove that root 3 is also an irrational number. Okay, so first let us assume to contrary that root 3 is rational number. Okay, so here we consider root 3 is rational number. So that is, we can find integers a and b. We can find integers a and b where b not equal to 0. Okay, such that root 3 can be written as a over b. Okay, so first we consider root 3 is rational number, but we have to show root 3 is irrational number. Okay, so here consider root 3 is rational number. So since root 3 is rational number, that is, we can find integers a and b where b not equal to 0. Okay, such that root 3 this can be written as fraction a over b. So root 3 is equal to a over B. And suppose A and B have a common factor other than 1. Okay, so if A and B have a common factors other than 1, then we can divide by the common factors. Okay, so that case we can also write root 3 as equal to S over T, where S and T are co-primes. Okay, so here we actually take this case, assume that A and B are co-prime. Okay, so A and B are co-prime. That means A and B have no other common factors other than 1. Okay, so A and B have no other common factors other than 1. That means A and B are co-prime. So now from this equation, root 3 is equal to A over B. So here you can cross multiply, then you will get B times root 3. This is equal to A. Okay, so B times root 3, this is equal to A. Now if you squaring both sides and rearranging them, then we get 3B square. This is equal to A square. Okay, so you get 3B square is equal to A square. Okay, so from this equation, you can say 3 divides A square. Okay, since 3B square equal to A square, so therefore A square is divisible by 3. Okay, and by the previous theorem, we know if P is a prime numbers and P divides A square, then P also divides A, where A is a positive integers. Okay, so here 3 divides A square. So by the theorem, it follows that 3 also divides A. That means A is also divisible by 3. Okay, so since A is divisible by 3, so we can write A, this is equal to 3 times C, where C is some integers. Okay, now if we substituting the value, substituting for A, so we know here we write A is equal to 3C. Okay, so now if we substituting the value of A is equal to 3C in equation 3B square is equal to A square. Okay, so then you will get 3B square, this is equal to 9C square. Okay, and if you simplify this one, then that is actually will give us B square is equal to 3C square. Okay, so B square, this is equal to 3 square, and from this equation, this means B square is divisible by 3. Okay, so this means B square is divisible by 3. Okay, and so B is also divisible by 3 using here theorem for P is equal to 3. Okay, so here P is equal to 3 is a prime numbers, and here 3 divides B square, then 3 also divides B. Okay, so here therefore A and B have at least 3 as a common factors, but we assumed A and B have no other common factors other than 1, but here we get A and B have at least 3 as a common factors. Okay, so but this contradicts the fact that A and B are co-prime. Okay, so this actually contradicts the fact A and B are co-prime. That means the A and B have no other common factor other than 1. This contradicts. Okay, this contradicts this fact. So this contradiction has arisen because of our incorrect assumption. So basically here our incorrect assumption is root 3 is rational number. Okay, so this is why we have arisen this contradiction. Okay, so we conclude that root 3 is irrational number. Okay, so this is how we can prove root 2, root 3 is irrational number. Okay, so now we will come back to class 9. Okay, class 9 concepts. So in class 9, we mentioned that the sum or difference of a rationals and irrational number is irrational number. Okay, so actually if we take this number, rational number, if we take as a 2, okay, if we take rational number 2 and irrational number root 2, okay, then if we add them, then you will get 2 times root 2 plus root 2. This is actually an irrational number. Okay, so 2 plus root 2 is an irrational number. Basically we can prove by using contradiction method. Okay, so 2 plus root 2 is an irrational number that you can prove by using contradiction method. So you can assume 2 plus root 2 is a rational number. Okay, then you have to you will get some consequences and will get contradiction. Okay, so you know this, and the product and the quotient of a non-zero rational and irrational number is also irrational number. Okay, like if we take product 2 times root 2, this is actually an irrational numbers. Okay, and quotient 2 by root 2, this is also an irrational numbers. Okay, so the sum or difference of rationals and irrational number is rationals. Okay, this is first point, and second point is the product and quotient of a non-zero rationals and irrational number is irrationals. Okay, so we prove some particular cases here. So here we prove so that 5 minus root 3 is irrational number. Okay, so in this example we'll show that 5 minus root 3 is irrational number. Okay, so here basically we can prove this is irrational number by using contradiction method. Okay, so first let us assume to contrary that 5 minus root 3 is rational number. Okay, so here we assumed 5 minus root 3 is rational number. Okay, so you know, for rational number can be expressed as a fraction a over b, where a and b are integers and b not equal to 0. Okay, so here we assume 5 minus root 3 is rational number. So that is, we can find co-prime a and b where b not equal to 0, such that 5 minus root 3 can be written as a over b. Okay, so we could able to write 5 minus root 3 is equal to a over b. Okay, and now if we simplify them, actually if we take it left hand side, okay, and we'll move it right hand side, then therefore we get 5 minus a over b, this is equal to root 3. Okay, so 5 minus a over b, this is equal to root 3. So now if we rearranging this equation, then we get root 3, this is equal to 5 minus a over b. Okay, so here the LCM is b, then this is actually equal to 5b minus a divided by b. Okay, so 5b minus a by divided by b. Okay, so that is actually root 3 is equal to 5b minus a over b. So since a and b are integers, okay, then since a and b integers, then a over b rational number, 5 is also rational number, then 5 minus a over b, this number is also a rational number. Okay, so 5 minus a over b, this is actually a rational number, but in left hand side, root 3, this is irrational number that we have proved in our previous example. Okay, there we have proven by using contradiction method. There actually we consider root 3 is rational number, and by definition of rational number, root 3 can be written as a over b. Okay, and then we get this equation root 3 times b, this is equal to a, and if we squaring and rearranging, then we'll get 3b square equal to a square, and from this equation we can conclude 3 divides a square, and by the previous theorem 3 divides a. Okay, and then since 3 divides a, then a can be written as 3 times c. Okay, so now if we substituting the value a is equal to 3c in equation, 3b square is equal to a square, then we'll get 3b square equal to 9c square, that implies b square equal to 3c square. Okay, and from this equation we can conclude 3 also divides b. Okay, so therefore a and b have at least 3 as a common factors, but initially we consider a and b have no other common factors other than 1. That means here this contradicts the fact that a and b are co-prime. Okay, so actually this contradiction has arisen since our assumptions root 3 is irrational number is wrong. Okay, so we can conclude root 3 is irrational number. Okay, so here, but in this equation we get root 3, this is equal to 5b minus a over b. But 5 minus a over b, this number actually rational number. Okay, and root 3 is irrational number. So irrational number. So here this contradicts the fact that root 3 is irrational number. So this contradicts has arisen because of our incorrect assumptions. Okay, so this contradiction has arisen because of our incorrect assumptions that 5 minus root 3 is rational number. Okay, so we conclude that 5 minus root 3 is irrational number. Okay, now we will show that 3 times root 2 is irrational number. Okay, so we can show as a similar manner. However, we show root 2, root 3, 5 minus root 3. These are irrational number. Okay, so let us see how to show this. Okay, so let us assume to the contrary that 3 times root 2 is rational number. Okay, so since 3 times root 2 is rational number, that is we can find coprime a and b. We can find coprime a and b where b not equal to 0 such that 3 times root 2 is equal to a over b. Okay, so 3 times root 2 this is equal to a over b since we consider 3 times root 2 is rational number. Okay, and we know any rational number can be expressed as a fractions a over b where a and b are integers and b not equal to 0. Okay, so that is we can find coprime a and b such that root 3 times root 2 is equal to a over b. And now if we rearranging, then we get root 2 this is equal to a over 3b. Okay, and we have already proven that root 2 is irrational number. Okay, so in left hand side this is actually irrational number, but in right hand side we have a over 3b where a and b are integers. So this fraction a over 3b is actually rational. Okay, so a over 3b is rational. So this equation actually follows root 2 is also rational. Okay, but this contradicts the fact that root 2 is irrational number that we have proven in our previous class. Okay, by using contradiction method. So here actually contradicts the fact that root 2 is irrational number. So we conclude that root 3 times root 2 is irrational numbers. Okay, so now we'll summarize whatever we covered in our previous lecture and in this lecture. Okay, so in this chapter basically we have studied first the fundamental theorem of arithmetic. Okay, so in fundamental theorem of arithmetic we have studied every composite number can be expressed as a product of primes. Okay, and this factorization is unique apart from the order in which the prime factors occur. Okay, so actually this if we have x is a composite number. Okay, so x can be represented it can be factorized as a product of primes as p1 times p2 times p3 times p4 pn. Okay, where p1 p2 p3 pn are prime. Okay, are prime factors. Okay, so x is equal to p1 into p2 into p3 pn. So now if we take p1 p2 p3 p4 pn as ascending order, that is if we take p1 this is less than p2 less than p3 less than p4 less than less than pn. If we take in ascending order, then this factorization will unique. Okay, so for example you can take a composite number. Suppose you take 50. Okay, so 50 this is actually a composite number since 50 has divisors 1 2 5 10 25 50. Okay, so here 50 has divisors other than 1 and itself. Okay, so 50 is a composite numbers. So 50 this number can be expressed as a product of primes. So 50 can be expressed as a product of primes. So actually here the prime factors are 50 can be written as 2 times 25, 5 into 5. Okay, so 2 into 5 square. So 50 can be written as 2 into 5 square. So this composite number 50 can be expressed as a product of prime factors. Okay, this actually said by fundamental theorem of arithmetic. Okay, and this factorization is actually unique apart from the order in which the prime factors occur. Okay, and second point, if p is prime, then p divides a square. Okay, so if p is primes and p divides a square, then p divides a, where a is a positive integers. Okay, and this theorem we have proven by using fundamental theorem of arithmetic. Okay, that actually we represent a as a prime factors. Okay, a is equal to p1, p2, p3 dot pn, and then we squaring a, then we get a square. This is equal to p1 square, p2 square dot pn square. Okay, and by the uniqueness part of the fundamental theorem, since the prime factors of a square are p1, p2, p3 dot pn. Okay, and actually the p actually one of the prime factors among p1, p2, p3 dot pn. Okay, so since p divides a square, okay, so p divides a square and p is one of the prime factors of a also. Okay, so p also divides a. Okay, so actually here we used fundamental theorem of arithmetic for proving this theorem, and this theorem is very important theorems that actually help us to prove root 2, root 3, root 5, this type of numbers is irrational number. Okay, and then we discuss to prove that root 2, root 3 are irrational numbers. Okay, and here we a note to the reader. You have seen HCF of three numbers. HCF of three numbers PQR times LCM of three numbers PQR, that does not equal to P times Q times R. But HCF of two numbers A and B times LCM of two numbers A and B, that is equal to product of A and to B. Okay, so this you know, this is important note. Okay, HCF of PQR into LCM of PQR does not equal to P times Q times R, where PQ are positive integers. Okay, so however the following results hold good for three numbers. So LCM of PQR, this is equal to P times Q times R times HCF of PQR. This is divisible by divided by HCF of PQ times HCF of QR into HCF of PR. Okay, and HCF of PQR, this is equal to P times Q times R times LCM of PQR divided by LCM of PQ into LCM of QR into LCM of PR. Okay, so student, I stop here this lecture. Thank you very much to all of you.